Thank you so much. You may be seated.
Thank you. Good evening, everybody. Very welcome here. I'm Cris. I'm the Vice Dean for Research and Postgraduate Students, and I'm standing in for our Dean, Professor Bertie Fielding, who is somewhere abroad at the moment. Okay, so my job here tonight is to welcome all of you, which I've already done. But let me start then with the most important person in the room tonight, Professor Lana. Welcome. And this is, I think, in anybody's academic career, one of the high points, if not the high point. So I'm sure he is going to enjoy the moment, I hope. And congratulations and very welcome. And then I just have to introduce or welcome also the lesser important people. So let me start with the procession. I'm going to start with Dr. Ronelle Retief, who is the registrar, and she's representing the rectorate at the moment. And then we have Professor Sibu Moyo, who is the Deputy Vice Chancellor for Research and Postgraduate Students. Then myself, but then Professor Ingrid Witsky, who is the Vice Dean for Teaching and Learning. Then we have Professor Gary Stevens. He is the Director of the Central Analytic Facilities, and he will actually introduce Professor Lana. I will call him in a moment. And then lastly, we have Professor Suzanne Fitz, who is the head of the Department of Earth Sciences, where Professor Lana is situated. Okay, so with that behind me, I think I just also have to welcome the people associated with Professor Lana, and firstly on that list is his wife. I think she is here tonight. There she is, Dr. Arihel Mazos, and then any other colleagues, friends, family that are here or watching online, very welcome to you as well. Okay, I think that is more or less my job that I have done. Now I'm going to call on Professor Stevens to please introduce Professor Lana.
Thanks, Ricky. It's lovely to see everyone here. Lovely to see so many students from the Department of Earth Science. Almost feel like we should start talking about coupled substitution in plagioclases. Seeing as we've discussed that a lot. Staff from the department and the rectorate and the faculty, thank all of you for making this possible. Cris is a relatively new addition to the university, and I think it took quite a lot of vision from the faculty and from Prof Moyo to see the opportunity that his potential employment here represented to the institution. So thanks for that. It was, I think, a brave thing, but a very good thing, and I think that having taken those decisions, it's wonderful to also then have the opportunity for you to experience a lecture by Cristiano about the research that he does. Just a few words about that. So universities depend a lot on what you can analyze, what you can measure. So much of what we do in the SET environments is determined these days by the precision of the measurements that you can make. And at our university, we've never really had a strong profile in research involving isotopes. This has changed dramatically over the last little while with the BioGrip initiative. This is a Department of Science and Innovation funded initiative. We now have fantastic facilities for measuring stable isotopes in water, which is a tremendous thing, enormously empowering in environmental research. That's a hugely important step. And now with Cristiano's appointment here, we have a person who's truly expert in radiogenic isotopes. So these are the isotope decay schemes that run continuously and are important traces of processes both in living organisms and in the environment. And Cris is going to tell us all about how we can measure these things using an enormous piece of equipment that the university, with the help of Department of Science and Innovation, has recently invested in, a multi-collector ICP mass spectrometer. And so we really are in a place with the appointment of Cristiano and with the acquisition of this new equipment. We really are in a place where we're leading almost in the world. My colleagues, who I have long collaborations with in France, are extremely envious of the equipment and the expertise that we have here now. So we were sort of behind them and relying on them, and now suddenly we're over here. And that's a great feeling. So a little bit about Cristiano. We have a sort of a weird parallel history in that I was at Wits University. Just when I was leaving Wits University to come to Stellenbosch, Cristiano arrived there and started his PhD there. So we didn't really overlap, except maybe for one or two departmental functions right at the end of when I was moving out and he was moving in. He then went to Imperial College in the UK, studied in London for a postdoc, and then we were lucky enough to bring him to Stellenbosch in 2008, if I remember correctly. And he worked here for a few years and helped set up the beginnings of our uranium-lead mineral dating facility. So these are these radiogenic isotopes. Then we lost him to Ouro Preto, and single-handedly, in a very, very difficult scientific environment, he built up the Laboratory for Applied Isotope Research, the AIR Lab, at the University of Ouro Preto in Brazil. He amassed an incredible array of equipment there, all on grant funding that he applied for himself and on funds that he raised from doing collaborative research with the Brazilian petroleum industry. Enormously impressive structure that we at Stellenbosch worked with quite closely. Students and samples from Stellenbosch used to go to Ouro Preto. Cris and I co-supervised a number of students between Ouro Preto and Stellenbosch, and then we were lucky enough to have an opportunity, coupled to the acquisition of this large multi-collector, to hire him. You really cannot accept government money for such a complicated piece of equipment if you don't have somebody adequately skilled and experienced to run the equipment. So when we got the grant, immediately started thinking, how do we get Cristiano here? How do we get somebody like Cristiano here? And there's a handful of people in the world who have the skill set. We were lucky enough to get him here, and I don't think you need to hear anything more from me. Welcome, Cris, and I hand over the microphone to you.
Okay, thank you. Thank you very much. Thank you, Gary, for the introduction. It was really nice. So Professor Moyo, Professor Schultz, Professor Ritz, Suzanne, Gary. So thank you all for coming. It's really nice and it's a pleasure to be here. And I really hope you enjoyed what I prepared for you tonight. So we're going to start with a little bit about isotopes. So I'm not going to talk about myself because Gary has already done that. So I'm not going to talk about how I got involved with PhDs or geology or where I did my PhD. So I'm just going to focus on what's been happening over the last 5 years in the Department of Earth Science, which has to do with the equipment that Gary's talking. And we're also going to talk about isotopes. So many of you know already that isotopes give us incredible tools to uncover the the hidden past of our planet. It gives us extraordinary tools, actually, and it put us at the forefront of science and technology to measure very, very precise chemical information of minerals, rocks, soil, and water, and pretty much anything that's made of atoms. And by learning how to decode this chemical information, we have the ability to tell stories about the geological processes that happened 2 billions and billions of years ago, or environments that we can reconstruct, and also we can track nuclear waste and talk about food security, all based on isotopes. We can go as far as dating the moon, constraining the age of planets, and the solar system. So my lecture tonight is about these stories, how we use isotopes to uncover the history of our planet. But before we go to isotopes, we just talk about this machine here. This machine is the one that measures isotopes for us. In many ways, this is the main reason why I was brought here from Brazil, as Gary said already. And for the case of Stellenbosch, this represents a multi-million investment, a multi-million rand investment. Not because of my salary, of course, but it's because it's the newest mass spectrometer of its class. It is the most precise, most sensitive, most versatile. And it can read pretty much anything about isotopes. So by learning how to decode these key information that is written in isotopes, you can actually tell different stories about these of the geological systems. And the isotopes that we measure with these machines are really, really precise. And for us geologists, this is more than a mass spectrometer. This is a time machine. With that, we can actually, geologists can actually time geological processes and time geological systems in the planet or elsewhere in the solar system. Now, and what's interesting about this machine is that we don't need a mountain of material to read isotopes or to measure as isotopes. We need just a grain from a rock or a speck of a powder or a laser hole the thickness of a human hair, and that gives us isotopes with great precision. If you want to know where this gemstone or this piece of wood or piece of liver is coming from, we do fingerprints, isotope fingerprint. And the cool thing is that you don't need much material. We measure with laser systems that barely scratch the surface of the material, so we hardly damage the material. And this is the data that we have when we measure these isotopes. So each point here is a measurement. So when we're reading isotopes from a sample, we do several measurements, and then we average them. And what we end up is a ratio with an uncertainty, which is a fraction of a percent. So you can see here on the side, so these are thorium isotopes. So you can see how many zeros behind the dot that you have. And this is the precision of the instrument. So this is the final ratio that you measure. So with that, you can use these isotopes to track nuclear waste. Like thorium isotopes are very important for tracking nuclear waste. And it's like measuring the thickness of a human hair, but from a distance of 1 kilometer away. That's how precise this machine is. So, and this is what we have in the department at the moment. We have a laser ablation system. It is connected to the multi-collector SPMS. Our samples, they sit behind here, this glass window, and we see whatever is in there from this light here. So we have the light imaging the sample right there. And the laser ablation, we can actually set hundreds and hundreds of spots and you can let the laser run overnight measuring. It go precisely on every spot. And the samples come from here and travel through this Tigon tubing here and goes into the ICP-MS. In the front here, you see two screens. So in this first screen here, we have a zoom out, we have the sample. In this case, it's a fossil, it's a shark tooth. And on the right screen here, we zoom in into the fish tooth. And that's where we see the texture of the fish. And in blue here, right there, is the spot. So with 100 micron spot size, you can actually analyze the material from this tooth. And with that, we can tell the age of the fossil. We can tell whether the shark lived in the ocean or had any contact with fresh water. We can tell about the diet of the shark. We can tell whether the shark the redox conditions of the water that the shark lived in. So all of that you can do with isotopes. And this is data coming from the machine already, so we're actually doing a lot of measurements and reading. So in this case here we have zircon minerals, right? We spotted them with 100 micron spot size, and we had done several spots here, and this is the result. Each spot here gives me a ellipse there on the diagram. And that you can see here by the variation in age. So we're constraining the age of these zircons. We have the variation of 334 to 338 million years. And the size of the ellipse represents more or less 3 million years, which is just 1% of the age of the grain. So with a spot the size of 50 microns, we constrain an age of 334 million years. So the average of all these spots, we get a final age of 336 plus minus 0.88. That means less than a fraction of a percent. So it's just a fraction of a percent. On the side here, we have half-unit isotopes. So you can see again, it's a very precise age. You can see the uncertainty here that's very, very, very small. And that is constrained with other spots, like 30 micron spots on each zircon as well. And on average, you end up with this ratio. So hafnium isotopes work together with the ages. We use these isotopes to tell whether the rock comes from the mantle, from partial melting of the crust, or whether we mix mantle and crust to produce the rock. We also can tell when the magma was extracted from the mantle. So we have two types of information here. One is the crystallization of the rock. The other one is when the rock was extracted from the mantle. And beyond geochronology, we can use isotopes to trace the movement of the elements through water, soil, life, atmosphere, basically anything. So elements like zinc, copper, lithium, calcium, iron, mercury, all carry a significant isotope signature depending on where it comes from and what process it's been through. So here we have two types of information. One is where the elements are coming from, whether coming from a factory, from the mountain, from the ocean, and the other is the process that we fractionate the isotopes. So by understanding the process of the environment or the geological process that they have been formed or in which they were fractionated. We can also use, for instance, isotopes to track pollution in the sea. We can use isotopes to track contamination from factories and so on. So isotope connects us with the biggest questions in science, whether it's through cosmology, geochemistry, geochronology, biogeochemistry, forensics, nuclear waste. So it tells us stories that stretch from the birth of the universe all the way to the future of our planet. And how do we measure isotopes? How do they work, right? Let's say you want to measure your tap water. You want to see contaminants on your tap water. All we need is 5 teaspoons of water. And then what we do, we suck the water through Tigon tubing and put them through this dome-shaped feature here that we call nebulizer. So we transform the water into a vapor, and then we get the tiniest particle of vapor, and we put it through the ICP-MS. So this dome-like feature here is a glass tube, and it sits right in the front here, and then it goes inside the instrument. So when the vapor goes into the ICP-MS, it hits a argon plasma that goes up to 7,000 degrees Celsius. This is hotter than the surface of the sun. So when you hit the vapor with the plasma, the vapor transforms into an ionized gas. So this gas gets ionized, and then it shoots into the ICP-MS in the form of an ion beam. So we have an ion beam coming out of the argon plasma, and it goes to the heart of the instrument. Right, so inside the instrument, this ion beam, we can actually direct this ion beam, bend it in several ways, and then split the ion beams into several beams. So we're going to have light ion beams and heavy ion beams. The light ion beams are going to travel inside the curves, the heavy ion beams are going to travel outside, and then they're all going to hit the detectors at the back of the instrument. So at the back there, we have a collector, which is a system of Faraday cups that measure the ion beams. So we have about 11 Faraday cups, and each Faraday measures an ion beam. In this case here, we have one ion beam for uranium, another ion beam for thorium, and other ion beams for the lead when we're doing uranium lead measurements. So that's what makes the instrument really precise, because we're measuring all the isotopes at the same time. And that's why we call this thing a multi-collector system, because we have several collectors that measure the isotopes at the same time. And what they do is they convert the energy or voltage that's coming from the ion beams into a signal, which is an intensity signal. So we measure each ion beam there is going to give me an intensity signal. And that's all the machine does. So it gives me the signal of the beams in terms of intensity. And what I do is I convert the signal into isotope ratios. And for that, we develop software to make life easier, because we do like hundreds of measurements during the day, hundreds and hundreds of measurements. So that's very difficult to actually do that manually, so we convert that using software. For that, we have to write the software, so the machine doesn't come with that, so we have to write this. And in the software, we actually do the measurement of the isotopes. In this case here, we see boron isotopes, and then the ratios, and then here you have the signal, the intensity of each measurement. So it's one measurement here, shown here, and the collection of the samples, we plot them automatically. And the interesting thing about this software is that while you're running the machine, we're actually visualizing the data at the same time. So you get the data and measure that. If you have any problems with the running of the machine, you stop the machine and restart it again. The other useful thing about the software is that the students can actually download the data, download the software themselves, because it's open, it's free, and they can learn how to use the isotopes from the scratch, from the data, from the raw data. Here's another application. We're doing carbon isotopes. So carbon isotopes is something very difficult. I never thought we would be able to do carbon isotopes before. So we can actually measure easily the carbon-12, carbon-13, do durations, and how the samples separate quite easily. Different samples will have a carbon signature. And that's for geochronology. Here we have the uranium, the thorium-uranium ratios, the ages, the uncertainties, and then here plotted, here's the final age of the sample. Everything visual, very simple to use, very intuitive, so students can actually do that quite easily. And the last application that we do is elemental mapping, so we can actually scan surfaces, not only minerals, but any type of surface, and we generate chemical elemental maps of the surface of the mineral. So here we can actually track the zonation or distribution pattern of the different elements on the surface. So we can actually produce different types of map on any kind of surface. Can be tissues, can be ceramics, wood, any type of surface, we generate maps. And we have precision as low as 1 ppm. So if you want to know the concentration of thorium on this zone here, I just put my mouse there, and then I can actually see the concentration of each zone. And this is the machine working. So the best thing about this machine is that they work at night. So we set the points, leave the machine at night, and then when the run is done, it shuts down on itself. So in the morning when you go to the lab, the data is already there like breakfast on the table, so it's just fine. So in this case here is the same mineral that you see here. It's being analyzed here at night. So this is the entire grain, and here's the laser going through the grain, analyzing, and at the same time, we see the map being generated on that side. That is with the software that we see here. So in the end, in the morning, you get the data very nicely there. So what we do with isotopes, right? So isotopes enable us to trace the origin of and sources of various materials and reconstruct the past and present natural processes. So some isotopes are going to work as clocks, and that we call radiogenic isotopes, and other isotopes, they work as fingerprints, and that we call stable isotopes. So one set of isotopes is going to give us ages, the other set are going to give you the sources and going to tell us where the elements come from. So how do we work with those things? Let's suppose you want to date a rock. So we're going to work with radiogenic isotopes. And when the magma crystallizes, so a magma crystallizes into a rock, so the minerals inside rocks, some of these minerals like zircon, they crystallize with uranium and no lead. So the crystal, a grain like that, will crystallize and will trap uranium in the structure. With time, uranium will decay to lead. And because I know the decay constant of uranium to lead, I can actually use this decay constant and measure the ratio of uranium to lead on the sample. So my job is to measure in the grains just the ratio of uranium to lead. And here, uranium is very good because you have two isotopes of uranium. One is uranium-235 decaying to lead-207. The other is uranium-238 decaying to lead-206. So when these two are the same age, and then it's because I have a very good system, and so I did a very good job at dating the grain, because the ages are concordant. So I can plot them in this diagram, which it's called Concordia diagram. So both ratios giving me the same age, and then you have a very nice plot here of the analysis along a Concordia line. So in this case here, we're seeing the same diagram with measurements from different machines of the same mineral. So here we have one machine that's called thermoionization mass spectrometry, and that gives the most precise ages. The problem with that, we don't have this machine here. So we have the next one, which is laser ablation SPMS. So it would be good to have a TIMS age, because it gives very, very precise age. But the problem here is that we digest the whole grain. So you have to get the whole grain and dissolve it in acid so we can actually measure. And then because we measure the whole grain, you have a very precise age. Now, if the grain is zoned, it's got cores and rims, an older core, a younger rim, and then when you dissolve the whole, then you get a mixed age, and then you get a wrong age. And so the next advancement in technology is the laser ablation system, where we can actually laser areas inside the grain. So the texture of the grain is very important. So we analyze the texture, and then in the texture I actually put my spots. And then each spot gives me a precise ellipse, and then the average there I get a very good age. So, and the other set of instruments is what we had before. We still use it, and most departments have it, but they are a lot less precise. The ages are good, usable, but if you have two geological events close in time, we wouldn't be able to separate them because of the precision. So we need a rather more precise instrument. So this is one here is ideal for geochronology because we can actually work with texture and we have a great precision. And that's how we tell the history of the Earth, you know, with geochronology, with dating minerals and rocks. And then without these radiogenic isotopes, we wouldn't be able to construct this. We wouldn't be able to tell that the planet is 4.5 billion years old. And we wouldn't be able to tell how the Earth was formed with the late heavy bombardment. We wouldn't be able to tell anything about the moon and how the moon was formed, because that we can actually date the moon, do isotopes from the moon, and we can tell that the moon came from the Earth. So we can also tell about the first continents that were produced with the Jack Hill zircons from Australia, and then with the first water, and then life, and then complex life, and then the explosion of life in the Phanerozoic, extinction of the dinosaurs, and then us here right at the beginning. So in the whole evolution, we belong to the last page of this history. So only right at the beginning there. But thanks to radiogenic isotopes, we can actually construct the whole evolution based on geochronology. Now, while radiogenic isotopes give us ages, other isotopes help us to construct or reconstruct the environment of the rocks or emplacement of the rocks. So isotopes like neodymium, hafnium, strontium, or calcium, they carry chemical information of magmas, sediments, crust. So the information about the mountain crust and geological process allow us to reconstruct the evolution of the planet. So with these isotopes here, we can tell whether the rocks are coming from the lower mantle or the upper mantle, or partial melting of the continental crust. We can also tell whether the rocks produce under a subduction zone or under a hot spot or under an ocean island. All of that is constructed with these isotopes here. A more detailed information about the mantle is when you get strontium isotopes against neodymium isotopes, you can separate all the rocks that are coming from the mantle. In this case here, we have continental rocks here. These are, for instance, you get the Karoo dikes, the Karoo basalts inside the continent. These are rocks enriched in strontium 87. And that, they're rich in that because they intrude and cross-cut the continent. So the continental basalts is because the mafic rocks from the mountain cross-cut the crust, it gets enriched in strontium. That's why they plot and form this huge field here. So on the other side here, we have the mid-ocean basalts that do not go through the crust, just oceanic crust, and are generated here. So they are not enriched, they are very depleted in strontium 87, but enriched in something that the mantle has a lot, which is neodymium 143. So then they're going to plot on this side here. And by tracking those things, we can actually separate the mantle and understand how the mantle works. It also tells us how complex the mantle is. Now, when a geologist is out there in the field, we don't see the rocks being formed like that. So we never see the rocks being placed. When you do the mapping, we see very weathered rocks covered by grass. There's no lake or water. We hardly can make any sense of the rock unless you do a proper geological mapping. But to get this understanding, or this level of understanding of the evolution of the rocks, we need isotopes and the geochronology so we can actually constrain the evolution of the planet. Now, if you want to constrain anything on the surface, the evolution of the oceans, the river, underground water, we do light isotopes. So we work with calcium, strontium, oxygen, lithium, boron. So those isotopes, they tell us how the ocean works and how the rivers work and how the underground water migrate through different water tables. So we can use these elements. So fossils like ammonite, trilobite, reptiles, they all carry chemical information in their bones. And we can use this chemical information to reconstruct the environment. So this is one of example that I'm working on at the moment. These are nautiloids. They are found everywhere, but they are specifically found in Morocco, and they're extremely well preserved. They lived in an ocean that was called, a long time ago, Pantalassa. This was the largest ocean that we had in the planet, and that existed around 435 to 425. So, and these fossils are so well preserved that they still have the shell preserved. The difficult part is to show whether this shell record any chemistry that relates to the ocean here. So what and the other interesting thing about this is that at that time, North America, Australia, China, they were all sitting in the equator, while us here in Africa and South America were all sitting in the South Pole. And that time, we pretty much were covered in snow, and the snow was starting to melt away, and then we have this large proliferation of life. So in Morocco here, so these rocks, they appear from south to north, all along here, what we call anti-atlas. So every black dot here in this area exposes well-preserved fossils like that. These are squid-like features. They have a conical shape, but just like squids, and they thrived in this ocean here at 420 million years. This is the anti-atlas reconstructed at 425 million years. So by looking at these fossils, the first thing that struck me is that they have a lot of uranium. So we could actually get a very good age of the fossil at 422. That, by dating just this shell here, the fresh portions of the shell, so we get an age of 422 MA. So we constrain the time that this creature was living. And then the other thing that I've done is getting a strontium. This data is from here. Those data come from the department. So we got a ratio here of 70-85. This ratio is very important because we have the variation of strontium of the water, of the ocean water, from 0 to 500 million years. So we can actually model this variation of strontium. And what we have here is that at 420, we have this ratio here at 70-85. So by having the age and the strontium, all matching the seawater composition at 400 million years, I can tell that this fossil is really, really preserved, extremely well preserved, and I can use it to reconstruct the chemistry of the ocean back then. Now, when you do the chemistry, when you use it, look at these elements here, right, of the shell, we have a very interesting pattern. And if I do now, go now and get some seawater from the North Atlantic, we get the same pattern, exactly the same pattern. So what we're seeing here is that the same pattern that we're seeing here 400 million years ago, we have it today. The question is how we interpret those things. One thing that we can see here that's quite clear is a cerium anomaly. So that has to do with oxygenation of the ocean. So it's a very oxidizing. When you have a lot of oxygenation in the ocean, we oxidize, and then we generate this anomaly. Back then, the living being was the nautiloids that were living there. They don't record this anomaly, and that tells us that they lived in a very, very anox environment. It's a lot less oxidizing. And from that, you can actually tell other stories. For instance, this peak here tells you how close it was to the continent, and so on. So, and then we can actually do further constraints on the chemistry just based on the shell. And with that, we can actually travel through and understand how animals migrated in the past and reconstruct animal migration in the present and in the past. We can also do tectonic reconstructions. So from one side, from the surface, all the way back to the crust, you can use isotopes. So they tell us when a granite body intruded, how a volcanic arc evolved, and then we can piece everything together to build the environments of emplacements, how the rocks are formed, how the continents are produced. And this is one of the examples that I worked with Gary for a long time. That's in Brazil. So Brazil and Africa were connected through the Congo Crater and San Francisco Crater. So this is one of the piece of lands that I worked with. So, and here is the same thing, just expanded. And this is the area that I worked most of the time. So my University of Rio Preto sits around here. Rio and São Paulo just about in this area here. So Rio and São Paulo are here. So there we have used isotopes and geochronology to reconstruct the entire continent. So these three brown blobs here, they form the backbone of South America. So they are actually the main piece of the continent that keeps the continent floating. It doesn't allow it to subduct. So in San Francisco Crater, once connected to the Congo, they actually formed a massive crater. And you can see by the level of the rocks are very old, they've been molten, they've been deformed, and they have been metamorphosed. The grains that come from these rocks are also extremely complex, and we only manage to understand these rocks is because you can actually laser the grains and laser the texture of the grains and get a very good idea of the age or any other isotopes to understand the evolution of these rocks. So with that, we can actually track the whole evolution of the terrain. From the initial stages of continental or oceanic crust, they start melting, producing granitoids between 2.9 to 2.8, and then you have subduction zones between 2.8 to 2.7, and then a massive collisional event at between 2.7 and 2.6. And with that, you seal the crater, you actually make the crater stable. And after that, nothing happened to the crater. So the crater doesn't record any other heating event, any melting or anything. So it's a sealed thing. It's done at 2.6 million years. And if you look at the sediments associated with these rocks, you can see all of them and date them and then track the evolution. And one thing that we saw is that these sediments around these granitic rocks, they record a similar evolution. So we can connect the magmas, the magmatism with the sedimentation. So now you're asking, what on earth am I doing with that? Why, how, what is the implication? What is the main implication and what is the benefit to society? So by knowing those things, knowing this evolution of these rocks, we can set target to mining and mineral explorations, and you can understand a little bit more. So geologists need to understand those things first, every step of the terrain, before they go out there in the field and then start looking for mineral deposits, strategic minerals for industry, and so on. So with that, we can actually build and plan how we develop mineral exploration in the country. And the last one, this is the last example, and this is the work that I've done with the oil industry. And of course, the oil industry was interested in dating the rocks and to track the oil fields and understand when oil was actually accumulated. And that was around here, near Rio. And of course, one of the spin-off of that work is the time of separation between Africa and Brazil, or Africa and South America. So all we knew before is that the opening of the South Atlantic started here. So we opened the separation between the two continents at around 135 million years ago. So that was the beginning of separation. And with that, we have volcanic rocks that spread all over around here. We have some volcanic rocks around here as well, all dated at 135. So that marks the beginning. The trouble is, as it opened, something happened here that the opening stopped, and that allowed the deposition of a major group of carbonatic rocks that we call rift. So these are rift-related carbonates. And then on top of that, we have this pink area here is a major salt layer. So this major salt layer traps all the oil that is in the carbonates below. And they seal that, and that's where we explore the oil. So till then, we didn't have the age of the salt. And the good thing about this salt here is that below the salt, we have continental carbonates, and above the salt, we have marine carbonates. So marine carbonates were deposited on top of the salt. The other cool thing about this salt layer is that we see that in South America and also in the African continent around here, Namibia. So the same oil fields that we have here, we're likely to have on this side. And by dating this salt layer, we can date the oil fields. We also can date the separation of the two continents, because just above the salt layer, it's already marine carbonates. So if we date the salt layer and date the marine carbonates, we actually time the opening of the South Atlantic. So here is a profile that you can see. It comes from here all the way to there. So here's a seismic profile where we have the basement rocks. These are Pan-African basement rocks. We see them in Brazil and in Africa. So covering the basement here in purple, we have the continental carbonates. So these were the carbonates that were deposited and produced the oil fields. On top in green here, we have this salt layer trapping all the oil fields. And then on top, we have the marine carbonates, which are in yellow here. So when you date these guys here, the continental carbonates, we get an age of 124 million years. So remember, these volcanic rocks of the Parana Basin intruded at 134 million years. And at 124, 10 million years later, we have the deposition of the continental carbonates. But that doesn't date the opening. The opening is the salt layer. So we were lucky enough to find carbonates inside the salt. So there are several layers of carbonates inside the salt where we dated and got very precise ages of 119 million years. So now we can say, okay, so we started the rift at 124 and the deposition of the salt layer at 119. And the carbonates on top here are 118 million years old. So we can actually track the whole evolution and separation between Brazil, South America and Africa from 124 with the opening of the rift stage. So we have the deposition of the continental carbonates, and then the deposition of the salt at 119, and then the opening of the South Atlantic between 118 and 116 million years. So what is the implication for that? We have many. First, we can understand how passive margin are evolved. We can talk about hydrocarbon exploration here in South America and in Africa. We can talk about plate tectonic reconstructions and also talk about ocean gateways, seawater chemistry. Everything depends on the opening of the South Atlantic. Even cooling of the planet is based on that. So we can actually really understand how things happen after the opening of the South Atlantic. Now, to close this, so we can, from the birth of the moon to the fall of meteorites, isotopes can connect us with the deepest history of our planet. So every crater on the moon, every meteorite that struck the Earth carries isotopic memory. So we can actually use this memory. By reading those signals, we can uncover the evolution of our planet. And that's it. Thank you very much. Thank you.
Thank you, Professor Lana. Good evening, colleagues and guests. Across cultures and centuries, people have been fascinated with the origins of the Earth and the forces that shape it. Our imaginations have been captured by myths of fire and flood, by scientific revolutions that revealed the Earth's vast age, and even by the stories told on the big screen. Films such as Ice Age and Jurassic Park simplify or dramatize the science, but they point to a shared human curiosity about where we come from, how our planet has changed, and what traces of that story remain. Perhaps it is this universal fascination that explains why a lecture on isotopes can capture the imagination even of those of us outside the field of earth science. Tonight, Prof. Lana has shown us that the real story is even more compelling than fiction. He has revealed how isotopes act as both clocks and fingerprints, transforming the tiniest crystal or fossil into a time capsule of Earth's past. Radiogenetic isotopes allow us to measure deep time with extraordinary precision, from the crystallization of minerals to the age of the moon, while stable isotopes trace the chemistry of ancient oceans, rivers, and atmospheres, even capturing the conditions of life recorded in fossils. What makes this work especially striking is its reach. Isotopes extend beyond geology to cosmology, biogeochemistry, forensics, and even the tracking of pollution and climate change. They allow us to read stories that stretch from the birth of the universe to the future of our planet. And this is made possible by the exceptional infrastructure now housed at Stellenbosch, where instruments of extraordinary sensitivity and precision enable researchers to turn microscopic signals into histories of the Earth and its processes. Prof. Lana's own career also reflects breadth and depth. From Brazil to Johannesburg, London, and back to Stellenbosch, he has advanced our understanding of tectonic evolution, supercontinents, and mass extinctions. Just as importantly, he has invested in developing laboratories, analytical tools, and above all, people who we have here in the audience tonight, mentoring the next generation of earth scientists in Africa and South America, and building collaborations across continents. In listening to this lecture, we are reminded that earth science is not only about the past. It equips us to understand the present and prepare for the future, whether in climate, resources, or the stability of our planet. Professor Lana, congratulations on your inaugural lecture. You have given us a new appreciation of the extraordinary stories written in the rocks beneath our feet. And you reminded us why earth sciences continue to captivate the human imagination.
Thank you very much.
Thank you.
So I won't keep you long. I know you're all eager to celebrate. Cris probably. A few words of thanks. Thank you very much, Dr. Retief, for these words. And first and foremost, of course, thank you, Cris, for choosing to join us, and then for this fantastic lecture. Very informative, very engaging. I didn't think I would still see something new tonight. So thank you for that, and I feel like we do need to appreciate here the isotopes, right? So thank you, isotopes. And thank you, scientists who came before us, who got us where we are today. So I'm looking forward to keep working on this, seeing the exciting future that the isotopes and the equipment gets us in the future years. And thank you, faculty and university, for believing in these kind of investments. The few million rands, right? That got us here. So thank you very much, of course, to everyone who attended here today, tonight, in person and online. Thank you, staff who came today. Thank you, Prof. Moyer, our DVC, then our Vice Deans, Prof. Afriki Scots and Ingrid Roritsky, and also, of course, Prof. Gary Stevens for the words at the beginning. staff of the department. I'm particularly pleased to see so many of our early career researchers here tonight. I think it does speak to the culture that you have set up. And I'm particularly pleased to see our undergrads here. Right? And I promise there's no test tomorrow. So thank you for coming. But then I do want to thank those who work tirelessly behind the scenes, those who make these celebrations possible, many of them this year. And so we have a few from our corporate communication marketing, and I have my list here. Amir Brown, Krista Davids, Chima Giacala, and Jonathan Day Blankenberg making this happen. And then for streaming, so that our online audience can also see, and looking at afterwards, Justin Alberts, and our photographer, of course. Thank you, everyone, for being here tonight with us. Thank you, Cris, for this fantastic lecture. Thank you, Cris family and friends. Time to celebrate, I think, so I invite you all to have some light drinks and cocktails outside. Thank you.
Thank you, Prof. May you all rise as the procession leaves the room.